Hey, today we will start a new chapter. This is about topology optimization. We will talk about the fundamentals of topology optimization first, and then discuss a specific methods on topology optimization, which is abbreviated as SIMP, solid isotropic material panelization with panelization. We will discuss the details of this method, and then later I will be talking about genetic algorithms in general, and then discuss how we can employ genetic algorithms to perform an topology optimization, let's say, task. Let's continue with the slides. You see there's a sketch, and at the beginning of this design, we have such a chair. But once you apply some of a kind of an topology optimization algorithm, and at the end of the steps, at the end of the iterations, the result is this one. As you see, it's using much less material than the initial design, but still is functioning the same. It's still a chair, still you can sit on it, and it can carry some amount of load, obviously. So the thing is that the function of the design is the same, the part is the same, but we are using less material. So this is actually the motto of topology optimization. You need to update your design so that with less material, your design can do the same task. And in actually optimization, what we are doing, we are optimizing the material layout. This is the most important part of the topology optimization. We are trying to use less material, and we are distributing this material in the design field so that its function will be as good as the initial design, and also it will use less material. So at the beginning, you need to define a design space, you need to define the loads, the direction of the loads, the amount of the loads. For instance, for this chair, we have some loads here, and also we have some loads on the back side, and we need to provide some values for these loads, and then our algorithm will work on these and try to optimize this material layout. And other things we need to define at the beginning are, for instance, the boundary conditions. This chair shouldn't be moving, so we need to have some points fixed. And in this problem, as you see, we have 4 corners fixed. We need to have material. This chair should be touching the floor from these 4 points. And you may further have other constraints. There are various studies in literature. You may, let's say, put a constraint on volume, put a constraint on strength, or other mechanical properties. It's up to your problem. And once you define all these and set your goal, then the optimization will do some iterations and try to improve your performance. And this performance might be strength, it might be, let's say, thermal performance of your design. It may be anything you like. The only thing is that you need to define the goal function properly. Let's discuss some more details about topology optimization. So once you mention about layout, this layout actually includes the topology of the shape, and the size of your structure. And in that structure, you have material distribution, and this material distribution will help you address all these problems at the same time. With the help of this distribution, you will be optimizing the size, you'll be optimizing the shape and the topology in general. Now let's have a look at the first one, the size optimization. What do we mean by size optimization? Optimization is not that difficult. You'll be given a shape, and the only thing you need to do is to decide on the size of it. It may be the thickness of a beam, it may be the length of a beam. It's just about sizing. So here you see an example here, an optimal thickness of an elastic plate, optimal member areas and truss structures. So it's not complicated, very simple optimization problem. Again, you will be given the design domain, and you're not allowed to actually change the shape of it. You can only change the size of the structures. You see this example here. We have a truss structure, and we have all these trusses. And as you see, after the optimization, this is the result. And this is a sizing problem, size optimization. We still have the same trusses, but some of them are thicker, as you see. This is the result of size optimization. And we are not actually removing any of these trusses. We are just making them thicker. Let's jump to the second optimization. It's called shape optimization. And the shape optimization, again, we do not actually modify the outer boundary. We just play with the internal shapes. As you see, initially, we have 6 holes, 6 circular holes, but right now these holes are changed. Their outer boundaries are modified a little bit. We don't have perfect circles. Instead, we have some modified shapes here, but the performance of these two should almost be the same. And the difference is that the one on the right-hand side is probably using less material. And what about topology optimization? In topology optimization, we have all these type of optimization. We can optimize the size, we can optimize the thickness. They are all included in the topology optimization. So since the topology is the general, let's say, geometry of the part, so we can modify anything inside or the outside of this given shape. So you see, you can change the number of items, number of holes. You can change their locations, change their shape, size. But the thing is that we need to also satisfy the connectivity in the domain. If you come up with a design, let's say you have one part here, another part here, and if there is no connection between these two, then it's not optimization. We cannot say that it's a perfect topology optimization. In the proper optimization, you should have connectivity between the parts. Here you see an example here. We have thinner, thicker lines, and we have some shapes, triangular shapes, and the size of them are not the same. So this is a perfect topology optimization example. So what do we know when we start topology optimization? We should be aware of the laws applied on our example. We should know the support conditions. Let me draw the same example here. So this is our simple supported beam. We have one support here, another support here. This is fixed support. So we know the applied laws. This is it. We know the support conditions. This is fixed. This one here. We have freedom in x-axis, but it's not moving in y. We should know the volume of the structure, and we should also know the design restrictions. For instance, if this is the 100% of the design, you may say that at the end of the optimization, you should have about 50% of the volume filled with material. That might be your design restriction. You may also have other restrictions, but this is a famous example, a popular example. And another thing, obviously, you need to satisfy the connectivity of these materials. While you are distributing the material, they should be all connected together. And in the optimization, actually, these are not represented by the topology, shape, or the size. They are all not represented with standard functions. We have instead some field functions, distributed functions, and they are defined in a fixed domain. We don't have any equations actually representing the shape, representing the topology, but instead we have a field function. You may divide your field into some grids, some smaller elements, and assign some values to these elements. So that's why actually we need to have some parameterization, or we call it as meshing sometimes, as you know. We need to divide our shape into smaller volumes so that things will be much easier and we can easily formulate the given properties. And the optimization, since we are mostly dealing with the strength and other strain properties, we need to define a kind of a stiffness tensor, and the optimization will be actually carried out according to the stiffness of your design. Here you see an example of an optimization in 2D. So this is this is a cantilever beam. So here we have a fixed support. This is connected to the wall, and here we are applying a load. It's a cantilever beam, and at the beginning we have this whole actually rectangle filled with material, but after the optimization, now you can see some steps of the optimization. Since in optimization, we cannot obtain the final result in just a second or just a single iteration. We have a couple of iterations, and after these, we obtain such a result. This is the result of the optimization. Let me show you the video once again. So you see we have some material in hand at first, about 30 or 40% of the volume is filled with material. So we are trying to distribute this material properly so that its strength will be as high as possible with a given amount of material. You see we have little modifications. These iterations are still carried out, but now it is finalized. And we stop at a point where there is not much change between the previous design and the current design. Let's have a look at 3D version of it. Again, it's a cantilever beam. This time, to make it actually faster, I used larger blocks. These are called as voxels. In the previous one, since it was 2D, we were using pixels. But right now, we are using 3D versions of these pixels, which are called as voxels. Let me start the, I'm sorry. Yes. Here you see after some point, we don't have much change actually in the topology. But at first, we have huge changes. And to the end of the optimization, we have little changes, and the optimization will stop once you don't have any other changes. Let me start once again from scratch. Here at this point, you can see that this is the first step actually. Since it's a cantilever beam, we are applying the force here. That's why we don't need to have material in this region. It's already optimized, but right now we have 3 disconnected parts. And if you remember, we said that the result of the optimization should be connected, and that's why actually our optimization continues. Now they are all connected. This part is fixed to the wall. Now at this point, we have a connection, a kind of a truss structure is formed in between these 2 parts. And we have another, as you see, another, let's say, truss structure is being formed, and it will be connected to this point. By the way, the colors are actually showing the material density. The black ones mean that the material inside these regions should have densities of 100%, and some gray parts are actually meaning that you have about 50% of material in these voxels. We always try to find some connected parts. We jump to the ends. Yes, it's finalized now, but you see these, we have a kind of a weird structure here. This is quite impossible to manufacture since they are non-manifold cases, if you remember from our solid modeling chapter. They are connected to an edge, and you cannot manufacture it by using the available manufacturing methods. So now these are all introduction. We will start discussing some details of topology optimization. And in topology optimization, actually, we can define our problem as minimum compliance design. We are trying to minimize the compliance, which means that you'll have maximum strength with the given materials. So now assume that we have a mechanical element, mechanical part, which is shown as omega here. This is our mechanical element. This one, this larger part. And you see we have some definitions. What are they? In all of these parts, we may have some fixed regions. So our part is actually fixed to the wall or ground from this region. We may have some traction forces. These are the forces. And we may have some body forces. In addition, we may have regions. These gray regions are filled with material, so they are kind of design points, which means that in the optimization steps, we are going to optimize this gray region. And we also have some regions where we are not allowed to distribute material. So this white region should always be empty. There shouldn't be any material inside this white region. And lastly, we might have some specific regions where you always need to have material. So this is a specific region where you should always have material. And we will be using these definitions in the upcoming expressions, upcoming slides of this topology optimization chapter. So now let's have a look at some formulations regarding the topology optimization. We can define our design problem as the problem of finding the optimal stiffness tensor. Since we are not talking about a single shape, we will be doing some discretization. And that's why we will always have some specific, let's say, stiffness values for each item. And that's why we will be using some tensors. And these are I and J elements of our, let's say, mechanical part. And this is our, as I said, stiffness tensor. And we are trying to define the energy of our part. And this is how we do it. Since it's defined over the domain, we need to take the integral. This is our stiffness tensor. We have the strain. And this is actually the integral term. We need to take the integral over the whole domain and obtain the final energy of our part under the given loads. So for the strains, we are using the linearized strain equations. And for the loads, again, we have a linear form. We have traction forces and we have body forces. If you take the integrals, then you can obtain the resulting force on this part. So we can actually define our minimum compliance problem as the maximum global stiffness. They are the same. If you are trying to minimize the compliance, then that means you are maximizing the stiffness of this part. And now we can represent the same problem in a different form. We are trying to minimize deflection of our elements under the given load L, and this will be under the given energy level. This is calculated using the previous equation we have shown. I did show you in the previous slide, and we have some explanations for the terms here. U is the space of kinetic admissible displacement fields of all the items in your part. And since there might be higher, let's say, displacements, if that's the case, then you should stop the iteration. The force might be too high. You have a limit for the displacements. And then we have body forces, boundary attractions, and AD is actually the admissible stiffness tensor. And your stiffness tensor should be a member of this, let's say, set. Otherwise, it will not be possible to have such an object at the end of the optimization. So we said that we are using finite elements, so we can say that this is the discretization step. And in this discretization, we have two fields of interest. The first one is the displacement field, the displacement of all the items. So again, let's have a simple discretization. You may consider the center of an item, displacement of it in two directions. It is 2D. So we need to have a displacement field, and also we need to have the stiffness field of these specific items. What are the stiffness of each element? And in order to make the things actually simpler, we use the same finite element mesh for all of these fields, for the displacement and for the stiffness. And we have such general equations. We are trying to minimize this actually compliance under the conditions. This is the main force equation actually, which can simplify as F is equal to K times X. This is our stiffness tensor, and use the displacement. So this should be satisfied all the time. In any step of your optimization, these equations should be satisfied. And the other one is about the stiffness, and the summation of all the stiffness, the stiffness of the elements should be equal to the resulting stiffness. So obviously key is the global stiffness matrix. So now let's have a look at the parameterization of the design. And we are trying to distribute the isotropic material. So this is our assumption. We are assuming that in each cell we have isotropic material. And now we are trying to find some elements which actually has material, and we will try to find some other which don't have material. So at the end of our optimization, we may come up with such a result. For instance, these ones will have material, and the empty ones will have no material. They will be void. And so we can say that this kind of a binary image, a black and white image.